Hello everyone, in this exercise, I will show you analog read with multiple channels using DMA. I will use register level programming. But I will use Cube MX only for clock configurations. Enable high-speed external oscillator. PLL source is external clock. System clock is 100 MHz now. Let's remove these confusing comments. These are prototypes of our functions. Let's start with GPIO configurations. There will be 4 channels to read. Channel 0 is connected to GPIO A pin 0, Channel 1 is connected to GPIO A pin 1, Channel 2 is connected to GPIO A pin 2, Channel 3 is connected to GPIO A pin 3. Enable GPIO A clock. Go to GPIO mode register. Set those pins as analog mode. Other registers may remain in reset mode. Firstly, enable ADC clock. ADC clock line is connected to APB2. And its frequency is 100 MHz. In STM32 which I am using now, ADC can work at maximum 36 MHz. We have to divide it by minimum 4 in this case. Now ADC clock frequency is 25 MHz. Resolution is 8 bits. That means, ADC values range between 0 and 255. Scan mode. Channels which I specified will be scanned. We have to enable it. Data alignment. I chosen right alignment. If I chosen left alignment, I would have to shift value 8 bits to right. Because data register is 16 bits register and there was going to be empty bits. Of course enable DMA mode. If you don't enable this bit, you can read values only once. But if you enable it, as long as new conversion completed you will be able to read new values. Go to sample time register 2. This register is about time of conversion. Here is a formula for time of conversion. I chose an 8-bit resolution. It is 8 ADC clock cycles. I chosen 56 cycles. The less sampling cycles the less time of conversion. 8 plus 56 is equal to 64 ADC clock cycles. In 1 second 25 million ADC clock cycles are performed. How many second is needed for 64 ADC clock cycles? Each conversion will last 2.56 microseconds. Go to regular sequence register 1. We have 4 channels to read. We have to write 3 for 4 channels. First conversion will belong to channel 0. Second conversion will belong to channel 1. Third conversion will belong to channel 2. Fourth conversion will belong to channel 3. First 5 bits represent first conversion. We have to make those bits 0. Second 5 bits represent second conversion. It will be channel 1. We will write 1 into them. Next 5 bits represent third conversion. It will be channel 2. We will write 2 into them. And lastly bit 15 to 19 represent fourth conversion. It will be channel 3. We will write 3 into them. Final step is to enable ADC. ADC configurations are over. Now let's go on with DMA configurations. Before starting configurations we should keep that in mind. ADC is connected to DMA2 stream 0 and 4. And its channel code is 0. Let's start by enabling DMA2 clock. Go to Stream Configuration Register. ADC channel code was 0. Priority level. There will be only one DMA request. That's why it is not important that much. But let's set it as very high. Memory data size and peripheral data size. Both are 8 bits. Memory increment mode. We enable it because we put data into array. Circular mode. We enable it. When the specified number of data are completed, it will point to beginning of array again, so that we will able to read new values continuously. Data transfer direction. Flow will be from peripheral to memory. I will not use interrupt. That's why I skip these bits. Stream number of data register. Shortly, how many channels are there to read? Stream peripheral address register. This is the address where we read data from. And that is ADC regular data register. There are two memory address registers. Memory 1 register is used when double buffer mode is selected. That's why I will use memory 0 address register. This is the address where we store data. Let's create an array for storing values. Final step is to enable stream. All configurations are over. Now we have to start conversions. Wait until first conversion gets started. Let's build and see whether there is an error or not. Great, no errors or warnings.